Positioning and collimation errors are the most common reasons for image rejections. But unnecessary retakes can be avoided by keeping your patient in focus, even when you're outside the room. My Exam 3D camera helps you to identify movements. With virtual collimation, you can quickly collimate or make collimation corrections at the workstation immediately before X-ray exposure. You don't need to walk back and forth, which helps reduce both walking time and the time the patient must remain still.
Let's explore visual mapping for X-ray acquisition using 2023 technology. Deep learning-based image segmentation could potentially be used to identify key anatomical structures in the X-ray images. These identified structures could then serve as landmarks for auto-positioning. When two cameras view a 3D scene from two distinct positions, there are several geometric relationships between the 3D points and their projections onto the 2D images. Before you run away, we're going to break that down into simple terms so you'll be able to see how the new modern 2023 auto-positioning actually works. The AI-based automatic positioning uses off-the-shelf 2D, 3D video camera that can determine distances in 2 points in its field of view. It displays standard red, green, blue video images. The automatic positioning software uses 2 deep learning algorithms with different inputs that produce comparable outputs to identify the landmarks on the patient's body. As I said, we want to begin simple, so I'll show you something that I used to use as a child, a little 3D viewer. And before that, people called them a stereoscope. It's simply a method to kind of fool the brain into looking at things as three-dimensional that are not. It basically takes 2 images and then puts them together as one image. Sometimes you've seen those books where you have the funny wavy lines and you have to move things in and out till it comes into focus and it becomes 3D. That's using this principle, stereo vision. 3D images using stereo vision has been around for ages. In fact, we've used this principle in radiology for many, many years. Another way of doing this without using the stereo viewer is kind of cross your eyes a little bit and then move your finger in and out till it looks 3D and then look at the 2 images. In fact, they used to have some glasses made up specifically for the radiologists that allowed them to focus in immediately and see 3D images. Try crossing your eyes a little bit and see if you can make out the 3-dimensional images that are shown here. There is a Towns view and a view of the abdomen with contrast media. Oh well, it takes a little practice and I'm sure you'll get used to it, but let's take an easier look at this. Here we see a 3D view of a stereo waters and you can see the anatomy very well. This probably dates me, but when I was working my way through college, I was working ER at night and I did a lot of stereo views for facial bones and gunshot wounds. So let's see how we've transited on our existing older technology utilizing the new digital imaging techniques we have today. In the real world, most everything is analog or continuous. In digital imaging, we need to take this analog real information, sample it, and break it down into numeric information. Using the data we've acquired, we can use a computer to reconstruct it into an analog image that is visual and can be displayed on a monitor. So as you can see, a digital image is not an exact snapshot of reality. It is only a discrete approximation. Digital medical imaging is a 2-part process: the collection of data concerning the interaction of some form of radiation with tissue, and the transformation of the data into an image. We record the data on what is called a matrix. If we have a two-dimensional matrix, the data is called a pixel. But if we use 3 dimensions, it is called a voxel. Intensity-based 2D, 3D registration methods rely on the pixel voxel gray values to reconstruct 3D poses of an object from 2D images with reference to a 3D model. Here we see a matrix made up of pixels. A pixel is the smallest addressable element of a matrix. The imaging receptor that we use in digital imaging is a matrix made up of detectors which detect the intensity of the X-ray in each one of the picture elements or pixels that you see. When X-rays interact with tissue, they create a density or intensity. The intensity of this interaction is recorded on the matrix. This is a process of recording the analog energy received. The analog information received will be transferred in the computer and analyzed to create a numerical representation of the intensities. This is called analog to digital conversion. The computer then takes the digital data, and that can be utilized with computer programming to create the images we see on the monitor. This is called digital to analog conversion. This image demonstrates this process where we're taking the analog information, converting it to digital information, taking that digital information and converting it back to analog or visible light that we can see on the computer monitor. It's very similar to, remember paint by number when you were a kid? You had the little drawings that were already outlined, and all you had to do was fill in the different colors or intensities, and you could create an image or a painting. We're doing the same thing here. To do this, we use what is called a histogram. So we need a histogram analysis, or an analysis of the colors or the paints that we're going to use, and where to place them. A histogram is an approximate representation of the distribution of the numerical data that condenses a data series into an easy interpretation of numerical data by grouping them into logical ranges of different heights known as bins. The image on the left is a histogram, and the highlighted area on the right demonstrates how the data is used and represented in the histogram. These sets of algorithms or computer formulas require us to firstly know the structural information about the image under the scanner. This includes pixel, pixel density, distributions, histograms, color distribution, and so on. Next, we need to have the structural information about the region that we're about to fetch from the image. This section deals with identifying our target area and how we want to be able to display the image. In other words, we can take the data and manipulate the data to visualize it how we would like to visualize it. Image segmentation divides an image into groups of pixels. Pixels are grouped because they share some local property, such as gray level, color, texture, etc. First, the computer must establish location of a collimated border of the image. It then defines the anatomic region. To do this requires a histogram analysis of the anatomic region. So image segmentation is the process by which a digital image is partitioned into various groups or subgroups of pixels called image objects, which can reduce the complexity of the image, and thus analyzing the image becomes simpler. The goal of segmentation is to simplify and/or change the representation of an image into something that is more meaningful and easier to analyze. This image demonstrates how a voxel is broken down into pixels and the pixels are arranged. You'll notice it corresponds with the axial, sagittal, and coronal reformatting process because it is a three-dimension or a voxel. We use various image segmentation algorithms to split and group a certain set of pixels together to form an image. By doing so, we are assigning labels to pixels, and pixels with the same label fall under a category where they have the same or some other thing in common with the pixels that surround them. We are able to separate the most required objects in an image from the rest of the not so important ones to create the image. This fundamental approach relies on detecting similar pixels in an image. Machine learning algorithms and classification detect similarities based on predefined known set of features. With these features, we can utilize the information via landmarks to make the automation process work and also to create different images from the data that we've received. Artificial intelligence uses artificial neural networks which mimic the brain. Convolutional neural networks are specifically used for the process because of their design to identify and process high-definition image data. These computer vision systems can logically analyze the constructs by extracting the most important sections and then organizing data through feature extraction algorithms and classification algorithms. Although neural nets are time-consuming when it comes to training data, the end results have been very promising and the application of these have been highly successful. This same technology is used in many applications other than medical imaging or radiology. For example, most facial recognition technology relies on 2D rather than 3D images because it is more conveniently matched a 2D image with public photos or in a public database. This is Mark Struthers. Thanks for your time and thanks for your attention.